Hello everyone. In the previous videos, we learned how the digital systems started. In today's video, we're going to learn about the number systems. But before that, I want to begin with a simple idea. The idea says that many scientific and engineering ideas are inspired by nature. Let's take some examples to understand this point. The airplanes. As you see, this airplane imitates this bird. That means that the birds have wings. The airplanes also have wings. The birds use their wings to control the movement up and down, left or right. The same principle applies on the airplanes. So this is just the first example. We have another one, the robots. If you look at these two pictures, you can say that robots can imitate animals like this one or humans like this one in their movement and behavior. Here the question is why I am starting with this point. I am starting with this just to say that even the number systems or some of the number systems are inspired by nature. For example, the decimal system. The decimal system is inspired by something we see and use in our daily life tasks. Let's prove this. First of all, just like machines, the decimal system is a human invention. People along the history invented how we count. They invented the symbols like 0, 1 up to 9. They invented how to add two numbers, how to subtract two numbers. And then they said that all of this is called decimal system, the decimal system. So the decimal system uses 10 symbols, 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 10 symbols and we can use them to represent any number. Let's say, for example, 97, 510, 670, and so on. So the question here is why 10 symbols? Why don't we use 12 or 8 symbols instead of 10? Why they didn't invent another 2 symbols? Let's draw any 2 symbols here. Let's say something like that. And let's say something like that, okay? So these are another 2 symbols. Why they just stopped here up to 9, not inventing another 2 symbols? Or why they didn't stop here and just used from 0 to 7, the octal binary system, the octal number system? The reason for that is many civilizations choose the base 10 because we counted on our fingers. And you know that we have 10 fingers, right? And we use these fingers in our daily life tasks, including the counting. So people said if we use these fingers in our daily life tasks, including the counting, then the system that we are going to invent should be based on these 10 symbols, these 10 fingers. And that's what they did. So that means that if humans had 8 or 12 fingers, our standard system would be different. We would have seen something like that instead of just from 0 to 9. Or we would have used like symbols from 0 to 7 instead of 0 to 9. Do we have a proof of that? The answer is yes, we have a proof. And this is our proof. The word digit in Latin means finger. So the word digit means finger, and so what is the relation between the finger, the digit, and any number systems? Any number system. Let's say any number, 97. Each number here is called a digit. The 7 is a digit and the 9 is a digit. So, and we know that digit is a finger. That is the connection. So the evidence here is, or this evidence is the first time that counting was connected the fingers. I don't want to say the first time. I just want to say that this is the evidence in which counting was connected to the fingers. Now let's move to the history of the binary system. In this slide, I am not going to explain the details of the binary system. I am just going to focus on its history. Before George Boole and his work on mathematical logic, and here I'm talking about logic, not number systems, there was a line of development that's related to the binary system. Early binary-like ideas appeared in China and India thousands of years ago. They were talking about something like two symbols or two lines, something like that. I'm not going into the details of this because I want to start from here, from this mathematician. His name is Leibniz, and this is his picture. This man formalized the binary number system. What do you mean by formalized? I have here a few points that explain what the meaning of formalized here. First, in 1703, he published work explaining arithmetic using 0 and 1. What do you mean by this? He was able to do addition, subtraction, multiplication, division on the binary system. Before that, people were doing these operations or these arithmetic operations on the decimal system. But no one thought about how can we do this on the binary system. So he was able to do that. He also showed that all numbers can be represented using only two symbols, 0 and 1. This means that he was able to convert the decimal values into binary values. For example, the 97, this is a decimal value. He was able to write this value as a sequence of zeros and ones. He was able to convert it from the decimal to the binary. So this is also impressive. He explained that this system works as a positional number system. What do you mean by this? Just like decimal, but instead of powers of 10, it uses powers of 2. Because in decimal we have a base of 10. So the weight of each digit has a base of 10, and we say 10 to the power of 0, 10 to the power of 1, and so on. But in the binary, we say 2 to the power of 0, 2 to the power of 1, and so on. I'm going to explain this in detail, so if you don't understand it for now, don't worry about it. He also showed how numbers can be converted between binary and decimal, not only from decimal to binary, but also from binary to decimal. And that is what we're going to discuss today and in the next few lectures. His work became a major foundation for modern digital systems. This is before George Boole. So why I didn't mention Leibniz in the history that I explained in the first video? Because we have two different points here. This man worked on, this man is Leibniz. He worked on the number system. This man worked on the logic. And I know that they are related, but the relation between them came after these two mathematicians, maybe by 70 or 80 years, by Claude Shannon, if you remember that from the first video. So this is before George Boole. I think George is wrong here anyway. So we can summarize all of that by saying logic represented mathematically. This is by Boole, and then Shannon. This happened in the 19th century and the 20th century. But numbers represented in binary, this is by Leibniz, and this happened in 1703. Now let's move to the next topic, the number systems. So now we know the history, we learned about the history of the binary system, about how the decimal system is inspired by nature. Let's now focus on the number systems, and this is the first topic to focus on designing the digital circuits or the digital systems. A number system is a method for representing numbers. I told you that we use 10 symbols for the decimal system to represent any number. If you remember, I mentioned 97, 510, and so on. So that is the definition. We use the number system to represent any number or any value. But I can say that this is not 100% accurate, because we can use the binary system to represent different data types. We can represent letters like A, B, C. we can represent sound like songs, images, and videos, and so on. So this is just the short definition of a number system. Early number system has a base, every number system has a base or radix. For decimal, the base is equal to 10, and for the binary, it has a base of 2, because this uses 10 symbols and this one uses 2 symbols, 0 and 1. Let's start with the decimal system. Here I am going into the details. I am not going to talk about the history again. So we said that decimal system uses 10 symbols, 0 up to 9. These symbols can be used to represent any number. We already mentioned this, but this is the first important point in this slide. The weighting factors, or the weights. In the decimal system, the weights are powers of 10, because we mentioned that the base is equal to 10. So the weights of each digit in any number represented by decimal, the weight is a power of 10. Let's look at how this looks like in real. Let's say that the decimal point is here. And this is the first digit on the left of the decimal point. This digit has a weight of 10 to the power of 0. This one has a weight of 10 to the power of 1, 10 to the power of 2, and so on. We are increasing the exponent by 1 while moving from right to left, starting from the decimal point. On the other side, we are decreasing the exponent by 1. So the first digit on the right of the decimal point has a weight of 10 to the power of -1, and so on. Let's calculate these values and represent them in decimal. 10 to the power of 0 is equal to 1. This is equal to 10, 100, 1000, 0.1, 0.01, and so on. Now let's take an example. Let's say that we need to read this value. Before that, let's say that this is the decimal point and the fractional part is 0, because we don't have a fractional part here. I am going to put each digit here under its corresponding position. So this is the first digit on the left of the decimal point. I'll put it here. The 5 should be here. The 6 should be here. Let's do this. As you see, 2, 5, 6. So why I am doing this? Just to say that this value or this digit has a weight of 1. What do you mean by a weight of 1? If you divide this into some ones, into a series of ones, we can say that it has 2 ones. Each one weights 1. But here this is different. We have a series of 5 ones. Each one has a weight of 10. And that's why the total is 50. The same applies to the 6. The 6 can be 6 ones. So each one of them has a weight of 100. And that's why we say that this is 600. Let's look how we read this value. When we read this value, we say 652. We don't say 652. If you say this, that means that this value has a weight of 1, this value has a weight of 1, and so on. I know that in some cases we say this just for a quick response. Let's say, for example, 1703, we say 1703. So sometimes we say it like this, but the correct one, we say 652. So let's do something here. Let's multiply each digit by its weight and do summation. So I'm going to multiply 6 by 100, 5 by 10, 2 by 1, and I'll add all of these values together. So the equation will look like this. 6 times 100 plus 5 times 10 plus 2 times 1. If you calculate this equation, this value, you will find that this is 600 plus 50 plus 2. This is equal to 652. You can see that this value is the same value as this one. So you might wonder that you might say we didn't do anything. We are just re-representing the same value again. That's right, but I'm explaining this just to say that we have a rule here that can be applied on any system. It can be applied on the decimal itself, like we did here. It can be applied on the binary, on the octal, on the hexadecimal, and so on. What is this rule? The rule says if you do summation for all, multiplication of each digit with its weight. So we multiply this digit by its weight, this digit by its weight, this digit by its weight, and we do summation between them. This is the notation for the summation. The output of this equation is a number in the decimal system, in base 10. We read this and say number in base 10. Let's say this is 5. We say 5 in base 10. That means that we need to write here that this value is in base 10. So in the next slide, we will understand this rule more. So I mean, like it might be ambitious now, but let's look into the binary system. For the binary system, it uses two symbols, 0 and 1, as we mentioned. These symbols can represent any number, and we will know how. We will know how to represent any value from any system by the binary system. Not only the values, we will know how to represent letters like A, B, C, and so on. Before moving forward, I just want to explain this graph here. In one of the previous videos, I said that 0 here in logic, in the theoretical logic, represents 0 volt in real, in the hardware, and 1 refers to 5 volts. But actually, this is not 100% accurate. The actual values for 0 and 1 are ranges. They are represented by ranges, not specific values. Because if you say that 1 is only represented by 5 volts, who guarantee that the power supply will remain stable at 5? If there is any discharge in the circuit, it can go down to 4.9, 4.8, or it can be 5.2 or something like that. That is why these values refer to a range instead of a specific value. And by the way, this goes back to the ICs and the transistors and how the transistors work. I'm not going to explain this. This is an electronic part. But if you remember the base, the emitter, the collector of the transistor, you would understand that if you put a range of values on the base can work on this range of values, not only 0. It can work on values from 0 to 1.3, providing the same operation, the off state, for example, or the 0 state. But if you put values from 3 to 5 or from 3 to 6, the transistor will work in the on state, okay? So the 1 can be represented by a range, maybe from 3 to 6, maybe higher values, maybe lower values, depending on the transistor type we are using. The logic 0 refers to a range from 0 to a specific value, let's say from 0 to 1.3, 1.5, and so on. Anyway, let's go back to our discussion here. Each position represents a power of the base, and the base here is equal to 2. What do I mean by this? This means that the weights here are powers of 2 instead of powers of 10 like in the decimal system. We have something called MSB and LSB. I'm going to explain this, but let's first focus on the weights. This is our, should we say, decimal point? This is our binary point. I am used to mention this point as decimal point, and I was doing this mistake too much actually, but now I'm trying to focus. So this is called the binary point. The first digit on the left of this point has a weight of 2 to the power of 0. Then we have 2 to the power of 1, and so on. Here we are increasing the exponent by 1, and here we are decreasing the exponent by 1. Let's calculate these values. Here this value is equal to 1, this is equal to 2, 4, 8, 16, 32, 64, and so on. And then here we have this one equal to half, quarter, 0, 1.25, and so on. Now let's take an example like we did in the previous slide. This is our example 101.1. And by the way, if you don't write the base here, this is gonna be a mistake, because this value can be seen as binary, octal, decimal, or hexadecimal, because all of these systems have the two symbols 0 and 1. So if you don't write base 2 here, then we can read this as 101.1 like in binary. We can read it in decimal like 100.1 and so on. So if you do this in the exam, this is a mistake. Okay, so let's do this. So let's now put each digit here under its position, corresponding position. So this is what I'm going to do. We have 1, then the binary point 101. So this is the binary point 1101. Let's apply the same rule that we discussed in the previous slide. This is the rule. I'm going to multiply each digit by its weight, each digit by its weight, and the output should be in decimal. So this is how it looks like. 1 times 4 plus 0 times 2 plus 1 times 1 plus 1 times half. The output here is equal to 5.5. And here I have a mistake. Can you say what the mistake is here? You can look at this and think about it. The mistake is I should say that this is 5.5 in base 10. Because if you don't say base 10, then this value can be seen as, can we say binary? No, because binary has only 0 and 1. So it can be seen as octal, decimal, or hexadecimal. The octal has 8 symbols from 0 to 7. So 5 here can be represented by octal and so on. Anyway, I'm just trying to give you some ideas on some stuff that you can make mistakes about in the exams. So before going to the octal, I just want to mention the meaning of this. This is called the most significant bit, and this one is called the least significant bit. What do you mean by this? If you go here after the decimal point, this is called, let's focus on the MSB first. This is called the MSB, the last one on the left. Why it's called MSB? From its name, most significant. It is the most important value, because this is the largest value. When we go from right to left, we are increasing the exponent. So the last digit on the left has the largest weight. So this one has a weight of 8. This one has a weight of 4. So this weight is larger than this one. That's why we say this one is very important, the most significant bit. And you can apply the same on the least significant bit. Usually we use the MSB and LSB with the integer, but in my opinion it can be applied even on the fractional part. But if we have only integer, we can say that this is the LSB, which means the least significant bit. It has only a weight of 1. Okay? So this is for the binary. Let's now move to the octal system. As you see, the octal system uses 8 symbols starting from 0, 1 up to 7. The weights are in powers of 8, similar to decimal, similar to binary, 10, 2, and 8. As you see, these are the weights, and I already calculated them in one step. So this is the octal point. 8 to the power of 0 is equal to 1. This is equal to 8, 64, 512. This is equal to 1 over 8, and so on. Let's take an example. 406.1 in base 8, and we have to write this base here. Let's put each digit under its corresponding position. So we have here the octal point. We need to write the 1 here, 6 here, 0 here, and the 4 value here. And let's apply the same rule. Let's multiply each digit by its weight. So 4 times 64 plus 0 times 8 plus 6 times 1 plus 1 times 0.125, and this is the final value, and this value is in base 10. So before I move forward, I have some notes here. You might wonder why the output of this rule is in 10 or in base 10 or in decimal system. Why it is not in hexadecimal? Why it is not in octal? Because when you wrote the weights here, you wrote them in decimal. So the 64 is a decimal value. I know it can be an octal, it can be a hexadecimal, but when you calculated this value, you calculated by the decimal system, by the decimal arithmetic operations. You said 8 to the power of 2 is equal to 64. If you want the output here to be in hexadecimal, represent this value in hexadecimal. It will not be 64, it will be something different. Okay? So let's say, for example, let's go back to the binary system just to show you something. Let's say 2 to the power of 4. This is equal to 16. The 16 in hexadecimal, let's say that we have a weight equal to 15 or 10. Let's make it more easier. 10. So when let's say this is equal to 2 to the power of something. This is a theoretical example. And the weight here is equal to 10. So we wrote it here 10. We didn't write the letter A, which is one of the symbols of the hexadecimal. So we are writing the weights by decimal. We are representing them by decimal. That's why the output here in decimal, not in hexadecimal, not in octal, and so on. And the 8 here does not exist in octal. So we can't say that this value is an octal because we used a weight equal to 8 and we multiplied 8 by something, and 8 is not a symbol in octal, right? I hope that you understand this point. Another point here. By the way, this is the rule. I'm hoping that you can see the rule now. So I am showing this rule in each slide just to make you remember it quickly. So in the exam, you don't need to think about it and how it looks like. And by the way, I intend to write it simply like this. Sometimes we have to write something like that, from I to something and end at something, and then we say J to multiplied by by Wi, and so on. I prefer to make it more simpler like this one. We have another note here, another notice here. Do you see this value? 406. This value is smaller than this one, 264. Actually, they are equal, okay? But I am talking theoretically. If we are representing both in decimal, this is 400, this is 200, okay? Again, this is in octal, this is in decimal, and they are equal, okay? But I just want to mention, if we say that they both are decimal, then this value is larger than this value, because you are moving from smaller number system to a larger number system. That's why the value here looks like smaller than this one. But if you move from decimal to hexadecimal, you will find the opposite. You will find the opposite in this case. So this is another rule. Another thing, for some cases you might have here 3 digits. When you convert them to binary, to decimal, you might see 2 digits here. That's also correct. But the opposite is not correct. That is really important. And this might assure you about your solution in the exam. If your solution here has 4 digits, let's say 1, 2, 6, 4, you might wonder why the same value in decimal has 4 digits, but in octal has 3 digits. This is wrong. It has to be 3 or less than 3, or smaller than 3, okay? Now let's move to the hexadecimal. The hexadecimal uses 16 symbols from 0 to 9, and then from A to F. As I mentioned, we have to use different symbols. We cannot repeat the same symbols again. So we used from 0 to 9, and we didn't say 10, because 10 consists of 0 and 1. So we need a new symbol. Do you remember the symbol that I drew like this? This is something like that. But because we have letters, we can use letters instead of inventing new symbols, and this is going to be complex. So we are representing the next symbol here by A, and then B, C, D, E, F. And we know that A has a value of 10. This is something we know, but we don't write it like this, except we are going to use it in an equation or in a calculation, in a mathematical calculation, like what we are going to see right now. The weights here are powers of 16, and this is how the table looks like. The first value after the hexadecimal point is equal to 16. The weight is equal to 16 to the power of 0, and this one is equal to 1. Then 16 to the power of 2, and so on. Let's take an example. 16A.2. Let's put each value under its position. So this is 2A, 6, 1. When we apply the same rule, this is how the mathematical operations look like. 1 times 16 to the power of 2, 6 times 16, 10 times 1. Here we can say A times 1. We can say A multiplied by 1, because what is the final value? The final value will be something like 16 plus A something plus B something. This is not going to work. So we represent the A by its value. So we say 10 times 1 plus 2 times 16 to the power of minus 1, which is equal to 1 over 8. The final value is equal to 362.125, and this is in base 10. You can see here that this starts by 1. This one starts by 3. So theoretically, this value is the 3 is larger than the 1, because we are moving. Sorry, this is another mistake. We are moving from the hexadecimal, a larger number system, to a smaller number system, which is the decimal system. Let's summarize all of this. This is our summary. We have 4 number systems. Maybe in the next levels, starting from now, including in this course or in the programming courses, you are going to deal only with 3 of them. We are not going to deal with octal. Only here in this course we are going to use it in the conversions, but after that we will not go on to use it at all. The binary has symbols 0 and 1. The decimal uses symbols 0 to 9. The hexadecimal uses symbols 0 to 9 and A to F. The base here is 2, 8, 10, 16. And to convert from any system, decimal, even decimal, binary, octal, hexadecimal, to the decimal, you need to apply this rule. Do summation to all the multiplications between the digit and its positional weights, and the output here is decimal. It is a number in base 10. This is the summary of our video today. I don't want to exhaust you with long videos. In the next videos, I'm going to explain the opposite conversions from. So instead of converting from any system to decimal, we're going to discuss how to convert from decimal to any system. And also here we have some circles like this. Let's say this is 2, 8, 16. We are going to learn how to convert between this, and also vice versa. So I think that's all for today, and see you in the next video.